1 minute to go. Okay, I think we are live now on YouTube. So let me paste the link here too. Please kindly share. Kindly share. 1 minute to go. Let me paste the link many times. So I've pasted it many times. Kindly share. Please share. Okay, if you can hear me on Zoom, can you write yes so that we now move on? Finally. All right, thank you. And let me share the slide. I'm coming. I want to share the slide. Let me do it this way. I'm still with you. Still with you. Okay, I will remove my video so that it will save you and me some data. So good morning, class again. And I thank you for joining. And welcome back to lecture 7 of this FSC 113, Introductory Computer Science. Last week, I hope you remember what we did. Okay, before I go on, well, I believe everybody can see my screen. 1 minute, let me see whether the YouTube people are there. My screen is filled up. How do I go there now? Okay. Yes, somebody is on YouTube. Hi, chat. If you're on YouTube, please kindly say hello, hi. But I will move on, and I hope that your hello, hi will arrive. Okay. Okay. So yes, I know somebody is writing me, sir, you muted us. Yes, I muted you. I purposely muted you, and I purposely made it such that you will not be able to unmute yourself. You will agree with me that's the best than leaving the place, making it to be like a market. Now, last week, if it was a small class, I would have asked, what did we do last week? But let me remind us more. Last week, we looked at computer processing modes and then computer networks. And under computer processing modes, we looked at the various kinds of processing, starting with real-time, batch processing, if you can remember. What is batch processing? What is real-time processing? The advantage, the disadvantage. Then we looked at others too, not only real-time batch. We looked at things like online processing. Remember, online processing. And there is something that comes to mind when you talk about online processing, the internet. We also looked at time sharing processing. We also looked at which other one, distributed processing, well, etc. Then the kinds of network, sorry. We looked at local area network, wide area network. We looked at client server network. We looked at P2P network. And then I remember us looking at network topology, the linear bus, the ring that you wear on your finger, and the star. Their differences, their advantages, and their disadvantages were considered by us. So today we look at, today's lecture will be on information representation. And under information representation, we are talking about how the computer represents whatever thing you are giving it. You are writing, I love you. You are writing, I no one see you. You are drawing. You are manipulating maybe an image. All these. How does the computer store, view it? You are viewing the words in English or in any language, but the computer does not understand our normal languages, our natural languages. Computer has its own language, which is machine language, which is binary number. So the computer deals in binary system. And of course, when you hear about the word binary, we are talking about zeros and ones. And zeros and ones, that's the only language via which the computer can communicate. So anything you write to the computer, for example, you write, my name is Simbi, computer will convert that to its own language. The computer will convert it to zeros and ones. The computer will convert it to its machine language. So that's what we are going to look at today. So have your pen and paper with you. I know some will say, I don't have pen and paper. So do magic to have pen and paper because we'll solve one or two things, very simple. Those that came into Unila with high JAM score, our X score, and at the same time, brain is not special center, then anything we are doing on binary, you should be able to follow up quickly. What are we going to do? We are going to convert normal decimal number to binary, and also from binary to decimal. If you are not able to complete it, then you complete it yourself. So that's why I should be faster with the theory part so that we'll meet up with the practical aspects. Okay. Please, I hope I'm loud and clear. Please let me know yes on the chat if I'm loud and clear. And be helping me also check the YouTube once a while, whether people are there and whether people are hearing. If there is any issue from that YouTube, let me know on time. Once a while, I will be posting the link to YouTube channel. I've posted it now. So please, once a while, share it because people will be joining and they wouldn't know. For now, Zoom is still open. And if you know you join with Zoom, please kindly share that Zoom link to others because we are just 39 here. You are seeing on the screen. Information inside the computer and on external storage devices is represented in a form related to the binary number system. So I told you that everything in the computer is in the form of 0 and 1. But not Sorry, network went off. So we'll continue where we stopped. As I said, once a while it will be going off, but we'll still come back. All right, so I continue. Said that every information inside a computer is in the form of 0 and 1. And not just computer, but storage devices, like your flash drive, disk, etc., hard drive, SSD. And in computer representation, a bit, or you call it binary digit, stores just 0 or 1 inside the memory. You know, some of our flash drive, or let me say hard drive, they come in gigabytes, 100 gigabytes, 20 gigabytes, even flash drive, you have 20 gigabytes. But the smallest of these units is what? Bits, B-I-T. Bits, that's the unit of measurement. Like in distance, most of you did physics, did mathematics. The unit of measurements of distance is what? Well, argue among yourselves, meter and kilometer. So is in terms of memory, unit of measurement is bit. That's the smallest unit of measurement, bits. And a bit can also be called a binary digit. A bit stores just 0 or a 1. So if I write number 100, can someone on the chat tell me how many bits will that take? If I say that a bit can take just 0 or 1, and I have this binary number, 100, how many bits will that number, 100, take? And someone writes it, 3 bits. Well done, David. 3 bits. 3. Thank you, Elvis. Thank you. That's all. Any other person writing 3 is doing expo. You have seen what others have written. Well, I'm joking. So it's 3 bits. So if I'm writing 1, 1, 1, 1, 4 times, that's 4 bits. So a bit stores just 0 or 1. Stores. Remember, bit is measurement of memory. What is inside your computer's brain. So it could be very big memory, but the lowest is bit. Sorry. And a collection of bits is called a bit string, as you can see on the screen. Bit string, one word, a collection. Like 100 I called is a bit string. 110101 is a bit string, a collection. But 1 is not a bit string. 0 is not a bit string. It's not a collection. But 01 is a bit string. 10 is a bit string. Now we move further. Second to the last sentence there. I think everything is clear there. A bit string, we know what a bit string is. That is 8 bits long. It's called a byte. If it is 8 bits long, it is called a byte. For example, 100, is it a byte? Yes or no? On the chat. 100, is it a byte? No, it is not. The answer is, the reason for why it is not a byte, because 100 is not up to 8 bits. But if you write any digits that are up to 8 bits, then it is a byte. You can't write 1, 3, 4, 5, 7. No, it must be only ones and 2 and zeros. 1 and zeros only. Any combination, absolutely any combination. But once it is 8 bits, then that bit string can be called a byte. For example, 1, 1, 1, 0, 1, 1, 1, 1. If it is 8 of them, is a byte. So 2 bytes will be 16 bits. 3 bytes will be 24 bits, etc. And a collection of 4 bytes, that last sentence there, a collection of 4 bytes. You know how from 4 we got 32 bits. A byte is equal to 8 bits. So 4 bytes will be equal to 32 bits. So a collection of 4 bytes or 32 bits is called a word. W-O-R-D. So if you can get any combination that gives you 32 bits, it's called a word. And you'll be wondering, why did we use 4 bytes? Why didn't we use 5 bytes? Why didn't we use 6 bytes? We used 32 bits because if you check the structure of computer memory, in the beginning when computers were springing up, the structure was in 32 bits memory each. Today we have a 64 configuration, 64-bit configuration. But that's not the case. That's not the main point here. The main point here is to know that 32 bits make a word, or 4 bytes is equal to 32 bits, and 32 bits is called a word. So bits and bytes, ladies and gentlemen, are important concepts in computer storage and data transmission. These bits and bytes, they are very, very important in computer storage and data transmission. Internally, that's inside, all modern computers represent information as bits. I told you that. And since a bit is the fundamental unit of information, the fundamental bit, that's the unit of measurement of information, is the smallest. So since a bit is the fundamental unit of information, then it is sufficient to represent all information. Since it's the unit of measurement, then it's sufficient. If you say kilometer is the unit of measurement of distance, then you can use kilometer to represent all kinds of distance. 10 kilometer, 20 kilometer, 12.5 kilometer, 0.5 kilometer, etc. So is bits with respect to measuring information, the size of information. And apart from that, bit is also the simplest representation because only 2 symbols are needed to represent 2 distinct values. We are not saying there are no other ways to represent information. After all, we human beings, how do we represent? We use decimal number when we are writing numbers, and we use alphabets when we are writing in languages, natural languages. So there are so many ways to represent information. But we are saying that with the help of bits, using bits, that's the simplest representation because you only need 2 symbols, which are what? Zeros and ones. So I move on, and I hope we are following. Okay. Let me wait a minute. May I ask someone who can type quickly? Why are there few people in this lecture? Is it your matriculation going on? Or is there a very major event going on by 8 o'clock this morning? Can someone quickly, while we move on? Oh, lecture-free week. All right. Exams are coming up, so we have to finish. All right. Most people didn't expect the class to hold, so they are probably in places where they can't join or didn't plan for it. All right, thank you. It's enough. Since I'm recording it, I will try my best to share the video link. But how do you get it? Because I can't be sharing it to everybody. I don't have access to everybody. So, do we have a course rep here of any department? Don't lie, you. Yes, Ugun, God of Thunder, will strike you now. If you're a course rep, okay. So, Ayomiki, you are the course rep, right? Of medicine and surgery. Okay. How do we go about? Okay. Let me let me see what I can yeah, message you directly, because if I write it on the general, they will take my number. 1 minute, please. Sorry, I was in a very important call. So Ayomikin, that's the course rep of MBBS. I will share the video link after the lecture. In case I forget, that's why I sent you my number. In case I forget, that's why I sent you my number. Don't call me. This is my WhatsApp number too. You write me on WhatsApp and introduce yourself. I will remember. Am I clear, Ayomikin? Sorry, I might not be pronouncing your name well. Okay, so I will send you this thing, and I'm sure you guys should have something like a group of a WhatsApp group for course reps, right? So if so, that's where you are going to share it. Yes, okay, that's where you are going to share it. Obafemi is laughing. That means maybe I did not pronounce your name well, Ayo. So let me just respect myself and just call you Ayo. Okay, so that's where the video link will be shared. So we move on. Data that we want to store can be alphabets now. Whatever we are writing can be in the form of alphabets. It can be in the form of numbers. It can be in the form of a mixture of alphabets and numbers. And then it can also be symbols. Anything you are going to type and check with your laptop, with your phone, it's either A to Z or any other language, or not necessarily English language, or it's numbers, or it's a mixture. Like those of you that like to write, form a password, the following day they forget it. So most passwords, they carry both alphabets and the numbers, and we call them alphanumeric. Then symbols, special symbols, like you can see them there, $sign, percentage sign, exclamation sign, at sign, quotation sign, question mark sign, etc. Okay, we'll move on. And then when we talk about characters, that's A, B, C, D, O. They are usually represented using 1 byte. And we know what 1 byte is. 1 byte is what? 8 bits. And there are 2 standard representation of characters. The next slide, we just see an example. First is the ASCII, and the second is the EBCDIC. The first one, the American Standard Code for Information Interchange. That's the one most laptops use today. You are not the ones going to convert. What do they do? If you type A, how does the computer interpret that A? As I told you, the computer does not understand A, neither does it understand T or S or Y or Q. It converts those characters to numbers. And there are already formula, or do I say table, used by computer to convert. So computer already know that A is so number. Computer already knows that B is so number. Computer already knows that D is so binary number. And that so binary number is either the ASCII they are using in the computer, that A is this, B is this, C is this, etc. Now we look at a table for you to understand what I mean for ASCII code. It might not be very clear. It might be zoom in. Now you see that small letter A in ASCII code is 097. You just need to ask, so how did they get 097? No, it is a formula already. It is an agreement already that A small letter should be 097. And see here, A capital letter is 065 in ASCII code. That is an agreement already. It is not something that we sit down and start calculating how is A 097. It's an agreement. B is 098. C is 099, etc. Small letter, capital letters. This is the ASCII code. Let me go back again. Here, C is ASCII. FCD also has this code, but most laptops today, they use the American standard. So which is what we are seeing here. So every alphabet in English has its name. So if you write your name, from your name, you can see that the computer will be able to convert it to ASCII code. But wait a minute. not converting it just as ASCII code. The computer uses binary, not ASCII code. So what happens? The ASCII code is converted to binary. So most part of this lecture will be on binary system, conversion from normal number to binary. Like this 097, how did we get from 097 to this binary? That's the major part of this today's lecture. How did we convert this to this? How did we convert this to this? How did we convert this to this? Etc. That's how are we converting these codes to binary? Right. Next. Now, assuming this is a text file, you can read what is written there. Spring is sprung, the grass has reached. I wonder where the flower is. The bird is on the wing, but that's absurd. The wing is on the bed. This is what a human being is writing, right? And how does the computer convert it? Now, see, let's start with the first word, spring. S is 83. P is 112. Let's go and check whether S is 83. S is 83. You can see it. Capital S is 83. Hope we can see it. Capital S is 83. The next one there was this. Let me check. Spring, P, small p. Let's go and check small p. Small p is 112. So just like that. You see how the computer has changed S to this, P to this, R to this, I to this. After that, what do you think computer will do? Computer will now convert these numbers to binary. 83, how do you convert it to binary? 112, how do you convert it to binary? And so on and so forth. Once a while, I will post the YouTube link, just in case, those that need it. Okay, so that's what we are going to do. First, let's look at mass selector. When you are preparing for your WAEC, preparing for your NECO, they were drilling you through these. What are real numbers? And real numbers can be integer or non-integer. So real numbers, it's hard to find a formal explanation of what real numbers are, other than to say that real numbers are numbers that you can find on the number line. If you look below this screen, below your screen, this is what we call a number line. And thank God you are still in 100 level, so you will still pretty remember, or it will still be fresh in your mind, what you did in SS3 or SS2 in secondary school about number line. This is a number line. 0 to your right is positive, to your left is negative. I think this is pretty clear. Now, real number is any number that you can find on this line. Any number that you can get, it's a real number. So, but that real numbers are integer or non-integer. So that's where the real stuff starts. What are integers? What are non-integers? So an integer, if I use a street language, or if I use a layman's language, it's a number that you can write a whole number that is not fraction. 10, 20, 30, minus 6, minus 7, minus 1 million, 7, 35. You see, these are whole numbers. Numbers that are written without a fractional component. That's an integer. Whole numbers. That one I think is easy to remember. Non-integers. That means they will be they can be written in a form of fraction to start with. So on the screen, the third sentence there, you are seeing that non-integer includes rational and irrational numbers. But before you read that, you read the last one. What are they? Sorry, before you read that non-integer includes rational and irrational numbers, you first ask yourself, what is a non-integer? A non-integer will be the opposite of an integer. And since we are saying that integer is a number that can be written without a fractional component, or simply put, integer is a whole number. A whole number, be negative or positive. Therefore, non-integer is going to be the opposite, something that can be written in form of a fraction. 1 over 3, 4 over 5, 6 over 7, minus 3 over 10. These are non-integers because they are like a fraction. Then these non-integers are again divided into 2. rational and irrational. And good 18, I have the explanation for rational and irrational numbers. See, rational number is any number that you can provide like a fraction, where the nominator, nominator is on top of the fraction. Sorry, the numerator is on top of the fraction. Denominator is below. If you have a fraction like 3/4, 3 is the numerator, 4 is the denominator. So if you have any number that you can express like a fraction, 1, wait, let's not rush. I'm explaining what is a rational number. There are two conditions. That number, you're able to express it as a fraction, 1, and the number 2 is the numerator is an integer, and the denominator is not 0. If you're able to write a number in that form, then that number is a rational number. The conditions, I repeat again. 1, a rational number is a number that you can express as a fraction, something over something, where the one on top of that fraction, in fact, and the one below, both are integers. That's number 1. And number 2, the one below, that's the denominator, is not 0. So that's a rational number. Bring any number. Can you convert it to be like a fraction? A over B, where A and B are integers, 1, and 2, B is not equal to 0. That's a rational number. Am I communicating, class? You can just write yes or no. All right. That's rational. Bring any number. Can you put it in form of a fraction where the one on top and the one below are integers, whole numbers, and the one below is not equal to 0? Then that's a rational number. Okay. Let me surprise you now. An example of a rational number. Do you know that 21 is a rational number? Yes, we know that 21 is an integer, but you can convert it so that it becomes a rational number. If I do 21 over 1, 21 over 1 is still 21. So 21 over 1 is a fraction. 21 is the numerator, is integer. 1 below is an integer, and that one below is not. Irrational numbers are numbers that you can't express as a simple fraction. The pi, that one is very, very popular. 22 over 7. It's an irrational number because it cannot be expressed as a simple fraction. Square root of 2 and the rest. So we shouldn't spend much time here. The takeaway here is, what are real numbers? They are divided into integers and non-integers. Integers are whole numbers. Non-integers are numbers that can be expressed as fraction, full stop. But under non-integer, you have rational and irrational. So rational are those, yes, that can be expressed as fraction, but where the numerator and denominator are integers, and the denominator is not equal to 0. While rational are numbers that you can express as a simple fraction. So this is the same thing I explained here, actually. So we move on. Then we've talked about representation of characters using the FSC code and FCD code. There's also one more term I would want us to know. We call it floating point numbers. And the real numbers are often called that. They are floating point. Reason is you can express them shifting the point in anyhow. Like, let's see on the screen, the original number we have is 123.45. And this 123.45 can be 1.2345 times 10 raised to the power 2. Well, you understand what I mean. You should have done this, or you change the points 12.345 times 10 raised to power 1, or this, or this, or this. If you check any of them, multiply it, will still give you this original number, 123.45. So why? So what is happening here? The point is floating. It was here before. We can put it here. Second, we can put it after the third digit. We can put it after the fourth digit. We can put it after the fifth digit. Provided the factor you are multiplying it with, the power is changing. So that's why it is called floating point number. And real numbers are floating point number. Any number you call, you can express it in the form of floating points. Like, let's say 50. 50 can be 0.5 times 10 raised to power what? Can someone tell us? 0.5 times 10 raised to power what? 50. 0.5 times 10 raised to power 50 is 0.5 times 10 raised to power. So people, Samuel, you are failing it. I will ask you for your department now so that we come there and laugh. 10 raised to power 2, not minus 2, not minus 1, not 1. 50 is 0.5 times 10 raised to power 2. Okay, final question. 50 is 500 times 10 raised to power what? 50 is equal to 500 times 10 raised to power what? Aisha, thank you very much. I think you are the first to answer. Oh, you are not the first, but I'm seeing your name first. Times 10 raised to power minus 1. So really, this class is not about teaching you this. I expect you know it because it will be needed. It will be needed very shortly. Get ready your pen, your paper. So if we have 2 bits, we can represent 4 possible unique combinations. And it's only 2 bits we are having. So you can see the unique combinations on the screen, 0001, 1011. There is you can think of apart these 4. If we have 3 bits, we can represent 8 different combinations. The 8 different combinations will be, we'll combine them. Do you understand what I mean? If you have 3 bits, you can have 100, you can have 111, you can have 101 or 010, etc. Find the combinations, you will see that you will get 8. Hope you understand. Then, if you have 4, you are going to get 2 raised to power 4 combinations. Like that. So in general, if you have n bits, you are going to get 2 raised to power n unique combinations. That means 8 bits. And remember what 8 bits are? 1 byte. Gives us 2 raised to power 8 unique representations, which is class. You just, with 8 bits, you're able to represent 256, numbers. And this is more than enough for our alphabets. Our alphabets, how many are they? 26. So that's why storage in decimal numbers turns out to be a wastage of memory. And that's why our computers, they don't store in decimal number. Decimal number, I mean the numbers you and I know, 1, 2, 3, 4, 5, 6, 7. Rather, the computer use store in binary, to save storage. Because binary system is more efficient way of representing numbers. Okay. Now, the binary number system. Decimal is on the left, which we humans use. On the right is binary. This is the table. If I put 10, you can convert 10. If I put 11, you can convert 11. But these are the basic ones. From there, others come. 0 is 0, 1 is 1, 2 is 10. How did we get 2 is 10? How did we get 3 is 11? How did we get 4 is 100? How did we get 5 is 101? So that's what we look at now. This table, we look at it. Before I close this slide to open my whiteboard, let me show us how we are going to move. Ladies and gentlemen, we first see how to convert the number to binary. I know most might know it, but some might not know it. We also look at how to convert decimal fraction to binary fraction, because in exams, you're going to have this. And you have to master it so that it wouldn't waste your time. Time will be moving in the exam, so you must, follow up quickly. Then third one, we do the opposite. The first two, we are doing decimal to binary. The last two, we are doing binary to decimal. The difference is that in the first two, we first convert a whole number, then a fraction. Then the last two, also a whole binary, then a fraction binary. So we move on to that now. I will close my slide. You can snap this. Well, I will still guide you. We are going to convert first a decimal number to binary number. So let me stop the slide and see whether I can share my whiteboard. I'm coming. Let me share whiteboard. Okay, please, if you can see the whiteboard on your screen, don't be afraid that your phone has spoiled. It has not spoiled. I'm sharing a whiteboard. If you can see, kindly say yes, sir. All right. All right, yes, sir, that's all. So let me write any number. Let me just write it here. Any number, absolutely any number. Let's convert 23. After converting 23, let's convert another number 5. After converting 5, we convert another number 9. Okay, I type this, but writing, I'll use my mouse. So bear with me. 23. I know all of you know a way you were taught how to convert your own. So let me use the way I was taught, if I can remember. 23. I'm using my mouse, so you bear with me. 23. You draw like this, Abi. You draw like this. So you are dividing by 2. That's the conversion from decimal to binary. You keep on dividing by 2 until the remainder is 0. You now take the remainder from down up. Well, you just see what I'm doing now. 2. 23 divided by 2 will give you 11. Remaining, this will take me time, but let me be changing the color. Remaining 1. 22, 11 divided by 2 again will give us 5. Remaining 1. 5 again divided by 2 will give us 2. Remaining 1. 2 divided by 2 again will give us 1. Remaining 0. And finally, 1 divided by 2, it can't go. So it's 0. So that 1 remains 1. We place an arrow to show how we are moving. We move down, up. We count like this, from down, up. So can someone quickly write on the chat what will be the answer? Quickly, quickly, quickly. Thank you. Thank you very much. I'm so happy that you are following. I know wherever you are now, you might be laughing at me. Look at this man. Doesn't know we know it. Well, all fingers are not equal. Some might not know it, so we have to, and it's part of the course. Now, 5. So let me shift my hand a little here. 5. Oh, wait. 5. Wait. Oh, it's still. All right. 5. So let's also go and divide. 5. So 2. 5 divided by 2 is 2. Remaining 1. This remaining one, watch. Some people say, sir, why did you write it here and not here? Let me remove. It does not matter. If you want, start here, no wahala. If you want, start here, no wahala. It changes nothing. At the end of the day, you're counting from down up. It changes nothing. So anywhere you want, it does not really matter. So the next 2 divided by 2 again, you get 1, remaining 0. And finally, 1 divided by 2. It can't go. So it's 0. Remaining 1. So we pick the answer from down up. And we get 101. You can also do 9. But I think that's pretty okay. These 2 we have done. That's pretty okay. Please, if you have a question here, kindly indicate. Don't be shy. Don't be afraid. Indicate. You ask, because I'm moving out now from conversion of decimal to binary. I've just done it. We've converted whole number decimal to binary. If you have any question, I give you 1 minute to indicate on the chat, or I'll move on. Okay, so I'll move on. So I'm filling this. What we've just done now is, can be jotting down. We've just done decimal to binary conversion. Decimal number to binary conversion. Now let's do decimal fraction to binary fraction. Decimal fraction to binary fraction. We are still converting, but now it is a decimal to binary. It's now, yes, fraction to fraction. But what we are going to get in decimal to will be fraction. Okay, so let me clear the screen. Let me clear it. I'm clearing. So let's take a number. I want to get a number that when you are dividing, it will end quickly. Yes, you might get a number that will be forever. 1 minute. Let me check whether I can open the manual. Give me 1 minute. Just a number that we can, okay, it's not even in the manual. Wait, let me just, I'll not be in the manual, a good one. Okay, I have a number, 0.625. Let me write it, 0.625. This is a decimal, and we have to convert it to binary. Now, remember when we did for whole number, we were dividing by 2. Now, for even number, for fraction, we will be multiplying by 2 until we get 0. So let's try it, 0.625. So let me go and write with my own hand now. 0.625. Sorry, that my 5 get big head. We multiply by 2. Not only multiplying by 2, well, I'll be showing you as we move. So listen. 2 times 5, 10. Write 0, carry 1. 2 times 2, 4, plus 1, 5. 2 times 6, 12.1. Now, when you are converting fraction to binary, that whole number, you keep it. It is no longer participating in the multiplication process. You keep it. So let me use a color to highlight that we are keeping this 1. So we keep on multiplying by 2 again, the fraction part, 2. It's multiplication we are doing. 2 times 0, 0. 2 times 5, 10. You carry 1. 2 times 2, 4, plus 1, 5.0 here. 0 is what we have. So we keep this 0 and move on with our multiplication times 2 again. 2 times 0, 0. 2 times 0, 0. 2 times 5, 10. 0. Carry 1. This is point here. 1. We take this one. And it's now 0. So we'll keep on multiplying until what the fraction part we are multiplying is 0. And at each stage, when you multiply the whole number, you keep it. It no longer participates in that multiplication. So at the end of the day, remember in binary, when we were doing the whole number conversion, at the end of the day, we chose from bottom up the remainders. But in this case, we are taking from up down these green circles. But since it's a fraction, the answer will be 0 point, then any other thing you have. Since it is a fraction, the answer will be 0 point, then any other thing you have, from up, down. When we are doing for whole numbers, we collected from down, up. For fractions, from up, down. So we'll have 1, 0, 1. 1, 0, 1. Yes, this is not a very interesting example because you might not know which one am I talking. Is it this one, this one? So, but I'm saying it clearly now. We are picking from up, down. This one first, 0 second, then this third. So, ladies and gentlemen, the binary equivalent of this decimal fraction is 0.101. How I wish I can get another example. The examples that you will get, you'll be multiplying and multiplying and multiplying, and it will never come to 0. But of course, have it in mind that in exam, you can't be given a number that it will never come to 0. No, you will definitely. Let's see one more number. I hope this number I'm writing now will come to 0 quickly. 0.375. It's a decimal number to be converted to binary. 0.375. So shall we go? Let's see. If I move a little and it's not ended, we stop. Okay. Times 2. So what do we get? No need showing everything again. I will just write it out. That will be, it should be 0.75. 2 times 5, 10. Abi. Or multiply with your calculator, Jerry. I think it should be 0.75, but let's multiply sharp. 2 times 5, 10. Carry 1. 2 times 7, 14 plus 1, 15. Abi. 2 times 5, 10. Let me not get it wrong. 2 times 5, 10. Carry 1. 2 times 7, 14 plus 1, 15. Yes. 2 times 3, 6 plus 1, 7. Here is 0. So we drop this 0. Not we dropping it. We just save it. I hope this is clear for now. Okay. If it's not clear, let me know. And check my multiplication. I hope I'm correct. Okay. Let me come again. 2 times 5, 10. I might even, let me make mistake somewhere and see whether you are even following. 2 times 5 is 10, carry 1, 2 times 7 is 14, plus 1, 15. Carry 1, 2 times 3, 6, plus 1, 7. Okay, we drop the 0. So we move on. Times, let me change the color to green back. 2. Multiplying. 2 times 0 is 0. 2 times 5, 10. Carry 1. 2 times 7, 14. Plus 1, 15. 0.1. 0. This one, you keep it. And you keep on multiplying by 2. Get 0. 2 times 0, 0. 2 times 0, 0. 2 times 5, 10. Carry 1. You put 1. Remember, this red we circle, it is no more participating. So you are not adding anything to it. So we have ended. So the answer is, the question was, find the binary equivalent of 0.375. So the answer is, first and foremost, 0 points. Since it's a fraction, 0 points. Then let's take our whole number from up, down. Up like this, down. So it will be 0, 1, 1. 0, 1, 1. So 0, 0, 0, 1, 1, 2 below. That's how it is sometimes indicated. It's equal to 0.375. That's the binary. So questions might come in different formats. Find the binary equivalent, or a number will just be written. And if you see these 2 below, that means it's already in binary. If I write 10, 1, 0, you don't know whether it's binary or decimal. So that indication will be there. If it is decimal, I think they put 10 below. Okay, we have done 2 things now. We have converted binary, we have converted decimal to binary. One was whole number, the other one was fraction. Now we are going to a different one now, the opposite, from binary to decimal. Any questions so far, please, kindly indicate. Kindly indicate. All right. No, sir. Okay. Let's move. So I'm going to clean this board. Now we have a decimal to binary. Let's first, sorry, binary to decimal. Let's first take the whole number, a whole number binary. A binary that is whole number. Let me just write in it here. Write it here. Let me take a simple one first. 1, 0, 1, 1, 0. This is binary. You'll be told it is binary, or you will see the number 2 below it. 1, 0, 1, 1, 0. So let's do convert to binary, to decimal. And conversion to decimal, you'll be multiplying. Remember when we are looking at floating point numbers. And every number, how do I put it now? Okay, before I, if you have this number, sorry, a number like use something draw. I'm not solving yet. I'm just using any number 1, 0, 1. Their position is what? Here is 2. If it's a binary number, that here is 2 raised to power 0. Here is 2 raised to power 1. Sorry. The number, I wasn't hearing. Let me call again to be very, very sure. Just a minute, please. Not going, but I'll be trying once a while. I think it's a very important call too. So here we have 2 raised to power 0, 2 raised to power 1, and here we have 2 raised to power 2. If I add something else, let me say 1, here 0, here 1. You will have 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, etc. Now, if you have a fraction point, let's say 0, 0, 1. Here will be 2 raised to power minus 1. Here will be 2 raised to power minus 2. Here will be 2 raised to power minus 3. Please, if that's clear, I have not answered before. Let another person that have not answered tell me that it is clear what I just did. It's the positions that I picked. All right, me on chat to say it's clear, please. All right. Let me see whether this guy will pick. Sorry, though, I'm still with you. I'm still with you. Need to call someone. I'm still with you. The call that said I should call. Just 1 minute, please. Please, I'm still with you. Still with you. I'm still with you, please. Making a call. Still with you. Hello? Okay. I'm back. So our question was, well, we had to convert this 10110 binary to decimal. So let me write out the number out. Let me clear this that I've written here so that it wouldn't confuse you. I'm clearing this I wrote here. 101. So let me continue. 0. That's the number we are converting. So you have to do multiplication, this number with its position, this number with its position. Here you have 2 raised to power 0. Here you have 2 raised to power 1. Here you have 2 raised to power 2. Here you have 2 raised to power 3. And here you have 2 raised to power 4. So conversion is what? This one, 1 times the power here, 2 raised to power 4. Plus this 0, 0 times 2 raised to power 3. Plus this one, 1 times 2 raised to power 1 plus 1 times 2 raised to power 1. And finally, plus 0 times 2 raised to power 0. So see what we did? 1 times this plus this times this plus. Sorry, the network. I hope I just pray this thing did not disappear. Seems it disappeared though. Let me see whether I'll get it back. Maybe we might be lucky. Whew, it's gone. It's gone. All right. Let me quickly write it again. 1 0 1 1 0. That's the number we are converting from binary to decimal. So here is 2 raised to, okay, let me start here. 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, and 2 raised to power 4. So we add this times this plus, etc. So this is 1 times 2 raised to power 4 plus 0 times 0 times 2 raised to power 3 plus 1 times 2 raised to power 2 plus final, okay, not finally, another 1 times 2 raised to power 1, and finally 0 times 2 raised to power 0. Please, can you see the screen? And so far, is everything clear? All right. Thank you, Chama. So we now calculate everything. Now it's simple. Everything multiplied by 1 is just the same number. 2 raised to power 4 will be what? 2 times 2, 4 times 4, 16. This will be 16 plus anything times 0 will give you 0. So you don't need wasting your time here. Plus 2 raised to power 4. 2 raised to power 2, 4. 4 times this is 4. Plus this is 2. Plus this is 0. So what do we get? Add 20, 22. 22. If we see this 10 below, it means decimal. Because someone now, we say, maybe size, not decimal, it's octal. Or it's what do you call hex system. It's decimal, 22. So you can convert any other binary whole number. Let me write another one, but I'm not converting it. Let me say 1, 1, 1. So this will be 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. So you have 1, or let me start here. 1 times 2 raised to power 2 plus 1 times 2 raised to power, well, let me do it here. 1 times 2 raised to power 2 plus 1 times 2 raised to power 1 plus 1 times 2 raised to power 0. Here will be 4 plus, here will be 2 plus, here will be what? Any number raised to 0 is 1. So remember it, please. Any number raised to 0 is 1. 5 raised to 0 is 1. 20 raised to 0 is 1. 1.5 raised to 0 is 1. So this is 1. So we get 7. This is 7. Okay. So we've been able to convert binary whole number to decimal. So finally, let's convert a fraction, binary that is in fraction form, to decimal. And that decimal is also going to be in fraction form. So I'm cleaning the board. So let me take one fraction. It's just similar, very similar. 0.01. We have to convert it to decimal. So maybe you will see something here showing that it is a decimal. So let's put our twos. Let me write it out here again. 0.01. Remember, here will be 2 raised to power minus 1. After the dots, you're having minus 2 raised to power minus 2. And so on and so forth. So you multiply 0 times 2 raised to power minus 1 plus 1 times 2 raised to power minus 2. Okay. This is equal to 0 times anything is 0 already, plus 2 raised to power minus 2. I think it's equal to 1 over 2 raised to power 2. You guys did this in maths. 5 raised to power minus 3 is equal to 1 over 5 raised to power 3. So negative, you bring it as a fraction and it comes down. So this is equal to 1 over 4. So you can convert it further if you want. 0.2, abi 5. Anyone you want to go, this or this. You see, it's a fraction. The original number binary is a fraction. When you convert it to decimal, it's also going to be a fraction. Let me do one more fraction and we are done. Let me write it here with another color now. 0.0011. So here is 2 raised to power minus 1, 2 raised to power minus 2, 2 raised to power minus 3, and 2 raised to power minus 4. So when we multiply, first 0 here, 0, anything 0 is going to be 0, but let's multiply it out for the sake of teaching. 2 raised to power minus 1 plus 0 times 2 raised to power minus 2 plus 1 times 2 raised to power minus 3 plus 1 times 2 raised to power minus 4. So here will be 0. This will be 0. This will be 1 over 2 raised to power 3. This will be 1 over 2 raised to power 4. Plus here, plus here, plus here. So add and get the answer yourself. That's 2 raised to power 3. That's 2 times 2, 4 times 2, 8. Which is 1 over 8 plus 1 over 16, I guess. So you complete the solution. Okay. Oh, you are saying that you can't see. Can you see my screen, please? I'm just seeing the message now. Can you see my screen? Someone else, can you see my screen? Yeah. So if you can't see my screen, it's your fault, I guess, because I'm still sharing the screen. Can I hear more people say yes? Let me be really, really sure that's okay. So if you can't see my screen, maybe check your connection, your network. Maybe it's from your own end. Or on the soft side, you can go to Mushin, take bus to your village, and go and start begging your village people that your screen cannot show anything they are teaching again. They should please forgive you. Okay, so we have done conversion from decimal to binary, whole number and fraction, and from binary to decimal, whole number and fraction. In exam, you might meet a number that is a mixture of whole number and binary. For example, if we have time to figure that out, for example, let me clear. This number, write it to 14.75. 14.75. This is a decimal number to be converted to binary. How do we convert it? Now see, first part is a whole number. See this one. 14 is a whole number. You know how to convert whole number decimal to binary? 75 is a fraction. You know how to convert 75? Whatever you get, you add, and that's all. Whatever you get, you add. I didn't want to do this, but just let me do it. This is a decimal number to be converted to binary. So 14, we convert 14, which is a whole number, 14. Remember how we learned conversion to binary, whole number, 2. 14 divided by 2 is 7, remainder 0. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. 1 divided by 2, it can go 0, remainder 1. So we take from down up. We get 1, 1, 1, 0. That's for 14. Now 75, which is a fraction. So let me come here and do that of 75. 0.75. We multiply by 2, remember? 5 times 2, 10, carry 1. 2 times 7, 14, plus 1, 15. So that one goes. Keep this one. We'll keep on multiplying times 2. 2 times 0, 0, 2 times 5, 10. Carry 1, 1. We stop because what we are now multiplying is 0, 0, 0. And we are taking from up down, starting with 0 points. So here we'll have 0.11. So and this is equal to, 0.75. So we add these two. We add these two, this and up here, this. We got 14, we got for 0.75. We add the two of them. So that would be 1, 1, 1, 0 plus this 0 point. So 0 point starts here. 0.11. This would be 1.0111. So this is the answer. I'm marking it good. So 14.75, the binary equivalent is this. Is that clear? Ladies and gentlemen, any questions, please feel very free to ask. I'm looking at this thing. Manual, yes, they showed few examples, I moved on. So here I'm just trying to be more elaborate. Okay, so if it is a number point something, take the whole number, convert it using the way it should be converted. Take the fraction, convert it using the way it should be converted, then add whatever you get, and that's it. Now, same with binary to decimal. And I'm giving this to you as an assignment. Let me clear. Let me write it here. 0, 1, 0, 1, 0.1101. This is a binary number. Please convert it to decimal. So this is an assignment for you. Take home for yourself. No need submitting anything, but it's take home. I can only add a few words here. We've learned how to convert whole number binary. Do it the same way with this. We've learned how to convert fraction. Do it the same way. It's the same, sha. Here is 2 raised to power 0, 2 raised to power 1, etc. going forward. While here is 2 raised to power minus 1, 2 raised to power minus 2, going backwards. So you'll be multiplying and adding. Multiply and add, multiply and add, you get an answer. And that answer definitely is going to be a decimal number with fraction. Okay, let me check your manual 1 minute. There is one more topic, but our manual was updated. So let me check whether the topic is there so that I don't go and teach you what is not there. Okay, 1 minute, I'm checking it. Okay, they didn't mention it more or less. Okay, but what I will tell you to go and look at is what we call binary coded decimal. Let me wait 1 minute and just get something. Yeah, binary coded decimal. I think they omitted it on the manual. Binary coded decimal. By binary coded decimal, I mean numbers being represented in fours, like 8. If you convert 8 to binary, you get 1000. That's 1000. It's already 4. It's fine. But if you convert 2 to binary, 2 will give you 10. It's not up to 4 digits. So in binary coded decimal, number should be represented in 4 digits. So 2, if you convert it to binary, it's just 10. To make it 4 digits, add 2 more zeros in front. It will be 0010. 3, if you convert 3 to binary, you will get 11, 11. But in binary coded format, it should be 4 digits. So that 1, you add 2 zeros in front, it will become 0011. Another examples like with 4. If you convert 4 to binary, it will give you 100, 3 digits. But binary coded format wants it to be in 4 digits. So 4 in binary, a binary coded decimal format will be 0, then 100. The takeaway here is any number you convert to binary must have 4 digits. If it is not up to 4 digits, add 0 in front, and it will be 4 digits. If it's already 4 digits, you are not adding anything. And check all the numbers we have. That is from 0 to 9. Because if you are converting 10, it's already more than 4 digits. But those basic 0, 1, 2, 3 to 9, convert, they will, some will give you 4 digits, fine. Those that like 1 will not give you 4 digits, 2, 3, 4. 5 will not give 4 digits. If you convert 5 to binary, you will get 101. So you add 0 in front to make it 4 digits. You know that any number you add a 0 in front, that number does not change. 50, if you add 0 in front, will you change? No. 1 million, if you add 0 in front, will you change? No. 3, if you add 0 in front, will you change? No. Same. Yeah. So any number you get in binary, and it's not up to 4 digits, you add the appropriate number of zeros in front to make it 4 digits. That's where you are dealing with binary coded decimal. Binary coded, C-O-D-E-D, decimal, BCD. That's the short form for it, BCD, binary coded decimal. There's an assignment I'm going to give you, which is also an expo. Okay, let me write it here. Okay, wait, let me share it on screen while you snap it. Wait, let me share my screen while you snap it. So I'm closing my whiteboard so that I can share it. Wait, I didn't get it right. Wait, I'm coming. Okay, these are about binary coded decimal. You can snap this. Let it be, an expo a little. You can snap a little when adding in binary coded decimal format. If you read it, you don't understand. Try to Google. Try to Google it. Let's see whether you'll be able to add in binary coded formats. I believe we have snapped this. The next, if you want to snap, fine, but you don't need to snap anything here. Here, see the normal decimal we have. The middle is the normal binary we have. Then the binary coded decimal format, you see, 4 digits. If it is not up to 4, they add 0 in front. If it is up to 4, you don't add anything in front. So the major challenge you have here is this slide now that you have already snapped, how to add in binary coded decimal formats. All right, so let it be an assignment, a take home for you so that you don't just go and enjoy your lecture-free week. And yes, congratulations on your matriculation. May your days here in Unilag be a good one, be a fruitful one, a successful one, be a one that where you are graduating either from here, Akoka, or from College of Medicine, your CGPA will be a one that you'll be happy to show. 4 points above, that would be great. And what else can I add? Yes, try to read your books, 100 level. That's the starting point. There are so many distractions. I did not get hostel. I was not allowed to ballot. I don't know where this office is. We are asked to buy this and that. Just take your time. Everything will be fine. Always tell yourself that others have gone. So is it me that will here? No, I will also graduate. I will also pull through. I will also through level. Not going to be easy. It's not easy because of where your exams will be at that you guys having some and you see how crowded experience, especially those with respiratory problem, asthma, etc. True. Others have passed through and had their good score. You also so read your books, but don't be the what do you call it again? Jack that jacks from morning till night with no. All right, sorry, we are through. Actually, we are through. I'm just admonishing us. Let's take serious with our studies and also socialize with people, get to know people. Life does not begin and end here. But at least know that no matter the fellowships you are in, no matter the associations you are in those associations in Unilag because first and foremost, you are a student here. If you aren't a student here, you will not belong to this and that association. So let's it also not take most of your time, especially in 100 level. 100 level, that's when you start building the foundation for your CGPA, for your GPA, for your performance. So all the best. Good luck. I'm not the last lecturer. I think Mr. Abbas will come in again. Let me see how it goes, but I'm not the next. I'm not the next, and I've done my own part. So all the best. Good luck. The course rep, MBBS, don't forget to say hello to me so that I will share the video and you share it extensively. The video is being shared because some of you are saying that today's lecture-free week and I can see many did not attend. So it will be fair to give them the video to watch. All right. Thank you very much. Have a nice day, everybody. Bye.